Okay, so last night, well, relatively speaking, this is a weekend, over the weekend, but I gave you this homework, and I get that there was, that I didn't really tell you very much about how to do this, so I'm going to give you a lot more help right now. Would you please draw right on your iPad a red arrow that goes from there to there and name it little a. Then draw a blue arrow from O to B and name it little b. And then draw a black arrow from O to C and name it little c. The questions were, how can you write AC but using only A, B, and C? Well, I don't think it'd take you too long for you to figure out that to get A to C to come out, it's pretty much, it's almost shorter than all of them. So is it even possible to take two of them and add them together and get that? No, you can't add A, B, and C together in any combination and get AC. So therefore, it must involve subtracting somehow. So here's a hint. And this really worked for me. Think of A, B, and C as streets that you can walk on. And then I added this little piece that I think makes sense. But they're one-way streets. So now, if you're going to go from A to C, do you get, we are not allowed to walk this way because, you know, that's just not one of the options. Who knows, maybe it's through a dangerous neighborhood or across a highway or something. So we can go on A and C, but if we're walking, we can probably get away with walking the wrong way down a one-way street. Do you get, we would need, if the pointy end is on this end, we need to go from here to there, and basically I'm saying some other way to get there. We already have the shortcut, it's AC. But what's the long cut? This way, which would be what? Negative A plus C. Negative A plus C. That's a lot easier way to think of it than C minus A, even though they're the same thing. Does that make sense to you, that I can reverse them and say it's C minus A? But it makes much more sense to think of it as I'm going to walk negative A, I'm going to go down this way, the opposite way as you're supposed to on that street, and then I'm going to walk down this street the normal way you're supposed to. So, given that, would you try to answer what's BC now? What's BC? How could you get from B to C only walking on the red, blue, and black streets? And remember, they're one-way streets. I'm trying to go from here to here. All right, I'd like you to check with the person next to you, rows 1 and 2, rows 3 and 4, rows 5 and 6. And if you don't know what's going on, ask them for help. I'll pause. Let me try this. Okay, so if you want to end up here, you start here and you have to get to here. Now that would be the shortcut. We already have that. We want the long cut. We want the way that's not the shortcut. So that would be to go down the street this way. That's negative B. And then down this street the normal way, plus C. Negative B plus C. Raise your hand if you had that one right. Okay, good. Now, question. That would imply magnitude. And we have both magnitude and direction on this. If I do this to it, that means magnitude of. And that means strip out the direction component, and all I have left is the length of the ray, and I don't want to do that, so no. All right. The next one is the midpoint of AB relative to O. Okay, I know that's a mouthful, so do you get what we're talking about here is a ray. Nope, not ray. What's that actually called? A vector. A vector that goes to the midpoint of AB. That's here. And it needs to go there relative to O, which basically means here's what I want it to look like. I want that. What? Okay. Would you agree that we need, it's kind of like going from A to B, except you don't go quite that, you don't go as far to get to this dot. So that's half of the distance from A to B. Let's just figure that out. What is half of the distance from A to B? Well, what's the distance from A to B? Again, you can talk about it in terms of how could I get from A to B? Let's say the question was just that. How would you get from A to B? What would you say? Negative A plus B, okay? Then, how would I get half that far? Half of the magnitude from A to B. And wait, from A to B, what was that directions again? Negative A plus B. That's half of the way to A, B. We use little a and little b. Go down this way and then up that way. And then if we go half that far, then we will have gone half the way. And then we need a way of saying to go from here to there. So it's basically I never delved into it this far in the last hour. I just talked about the magnitude difference, not the final ray. How do I get this to be back to a ray? I'm going to stop here and say that I know that was an interesting stretch on this question. We don't ask you anything like that. And so I think it's interesting enough to find the whole half of meaning midpoint of the magnitude, which we already had by doing this. So I'm going to stop there and say you wouldn't have to know any more about how to make that vector. I know it's kind of wimping out, but we have a lot to learn today, and that's not worth getting tripped up on because it's not important. What I'm about to do with you is, though, you have to be able to do it in 3D. Go to this problem. So, BC is a good question. I hope that's an easy one for you. How do you ride on just the red roads to get from B to C? Please compare it with the kid next to you and see if you get the same answer for just part A right now. Okay, so BC, you should have said negative B because we have to get from here to there. And so I take the long way, though, and down this way and back this way. So you said negative B plus C. Raise your hand if you got that one right. Okay, good. Now, let me just challenge you with this. If that's the answer for that one, what's the answer for that one? It's the same. What? Isn't it the same direction and the same length? So it's exactly like if I would have asked you this. So do you get if I give you one that's in a weird position that you can't really answer, that you should go, oh, that would be the same as that, which I can answer. That's what we do in part B. Part C asks you to go to H, which doesn't even exist on this drawing, so I'm going to remove it now, even though the H was technically here, but I'm going to have you skip part C. But try part B. AG is not one that you can do easily, but there's another one that's exactly the same that would be easy to do. I'll pause for a second while you try that. Okay, some help on this one. I get that AG is not one that you could probably do naturally. Here's AG, A to G. But if you use the symmetry of this box, then what's the exact same thing as A to G? C to E. Wouldn't it be the same exact length? Yes, sir.
I think it would be the exact same length, but if you...
But it might have the opposite direction. Okay, I'll give you that. And I just drew one that has arrows on both ends, so I kind of covered myself there. But does the, first of all, let's establish, does the direction matter on vectors?
Yeah.
Totally matters. So now we're changing this direction. So I think we can all agree, if you're thinking in 3D, okay, and let's say that this is like the X and Y and the Z axis is coming out this way, okay, that there is a direction now in 3D for these vectors, and the vector AG was heading from this way to that way, in kind of heading to, in our situation, it's kind of pointing towards the clock, okay, that way. So then, if I change it to this, would you agree that it's got the same length? How about that? Okay. Would you guess that it's got direction? Oh, this is interesting. I'm guessing the direction then. I'm wondering if it's a reciprocal of the slope of it. Ooh, that's going to get really complicated. How about we just get the distance? Okay, okay, you've got a good point that C and A can get us there. C and A can get us there, but they can't get us there directly by just simply adding them. Okay, so let's go back to this. So C plus A, if we can only walk on the C streets and the A streets, so to speak, is it going to be C plus A? I think it is. It's regular C plus A. I think you're right. Because let me show you. If I take this and I move it, that's ray A, right? Now this is not ray, vector A. Do you get if that's vector A? It's still vector A if I put it here. It's still vector A if I put it here. Now doesn't it look like C plus A? Well, yes. This is really important to understand. If that is cloned, that's the same exact vector. There is no difference because they're pointing the same direction. They have the same magnitude. What if it was over here? Same exact vector. I know that annoys you because you used to, whenever you move graphs around, their equation changed. Okay, but not vectors. These are identical vectors because I cloned it. They're the same exact thing. That's the same thing. That's the same thing. I can move it over here. Can I change its angle? No, can't do that. But these are identical vectors. So they're here, here, here. So, again, if it's here or it's here, they're identical to each other. Yes? A plus C would get you to the same exact place. So yes, A plus C is equal to C plus A, and that's important to understand about vectors is you can rearrange them like that when they're adding. Yes?
Then if you wanted to do BH, would you do negative B plus A plus
BH. Hold on. You are really obsessed with BH. Let me see if I can find it. BH. Okay. So the question is, and maybe class, you guys can help me with this, is he wants to know if you were going from here to there, how could you get there using only...
No, I think you can. Unless if you do.
Okay, what do you think?
So I had negative B plus A plus parentheses.
Okay, hold on.
B plus
Negative b goes this way. We're good so far. We're taking the long way to get here, right? That's kind of what the point of these things is.
Yes.
And then what?
Then I have parentheses negative b plus c.
Negative b would,
And then it just takes you up. So it would go from like here to here to there.
draw that again.
Here to here.
Here to here I already got. And then if I wanted to do this, you're just saying to go to A, I can buy that.
Yeah.
So I can say plus A.
And then if BC is equivalent to EH, because it's just the same vector, you just add that.
But it's not on one of the roads. But what is BC? No arrow on that end. What is BC? Negative B plus C. So then if you want to make this last piece be this piece, and it's called negative B plus C, then we'd have to do B plus A plus negative B plus C. So you could say that's A plus B plus C minus B. So then isn't that just A plus C again?
No,
I think this is interesting.
that's going to be
Would you agree that these should cancel each other out?
Yeah.
So then you're saying it's just the same exact thing as AC.
No, those don't cancel each other out because it's still negative B and then that's positive. It's going two different. But if I don't want to get rid of that because that's an angle.
It's a very good question, but if we put that on the test, only Strat's going to get it right. And of course, you'd like that, but yes. Okay, I don't want to go any further on this problem. You just said like 7 things. Couldn't you just do these 7 things? Probably, but I'm not going any further on this. We have new stuff to learn. Stop. Okay, moving on. Let's get to, actually there's a slide that's got, it's bright yellow right there. It looks like that. Representations of vectors. So, I'm glad you're asking questions. And they were very good questions, but if I spend too much time on them, you won't get enough time on the new stuff. All right. So I'm going to kind of cut this a little bit shorter so that it will still get to the same place. All right. So that blue vector there called A, do you get, I can write him in different ways? It's kind of like polar form. Polar form was only a dot. Do you remember that polar was just a dot? It was not aligned to the dot. I kept trying to remind you, the polar is just a dot. It's how to get to that dot. But this is not just a dot. This is this whole thing. This whole thing is a vector. And it starts at 0, 0, and it goes to that dot. Well, of course, that dot's still important. So how far over and how far up is it? It's over 5 and up 3. So, not too surprising that I would call it, if it's vector A, that it would be 5 to the right direction, which are called I when you're using vectors, plus 3J. And I'm aware that I seems like a terrible choice. They should have chosen J, K, and L or something. Because I implies imaginary. It's not in the context of a vector. An I is just the X direction. Okay, so this is the same as this blue ray right there. Not ray, vector. Jeez. Got that stuck in my head so badly because it looks like a ray because it's got the pointy end on one end. It looks just like a ray. Why isn't it a ray? Because it has magnitude and direction, and that's what makes it a vector. Okay. Good question. You aren't going to use your calculator on this test, but if you're going to put this in somewhere, there's a much more efficient way to put it in. 5, 3. Do you get how that still has the 2 main components that you need? How far over and how far up is the end dot, and yet it's quite different than 5, 3, because 5, 3 is a dot, just a dot, and this is the ray that starts at 0, 0 and goes to the vector that goes to 5, 3. All right, and then the cool thing is, everybody make a piece of graph paper appear on your iPad. I know you can do this. I'm going to add a page. I would do add page and then make the page be graph paper. Okay. Then I'd like you to draw that little vector and then write on there the two ways you could describe him. We're going to use R. We're going to make up the pirate theme. R is our vector. And he could be written this way or that way. One's more complicated and involves a couple letters. The other one just has numbers in it. Did you get 2I and 2J? And then the other one, this, by the way, is called a position vector, and this one is called a column vector because the twos are right over the top of each other in what's kind of like a column on a matrix. Get how these are kind of like matrices? Got this bracket with numbers in it? Okay. All right. Please draw this picture with me. I really think it's going to help you understand this better. Okay, now next, we're going to draw one that's a little simpler. It's going to be, pirates like to sail on the sea. And so the C is going to be a different vector that goes just 3I. I can put plus 0J if you want. Would you write me the column form for that and also put it on your little picture? This one was R. Do you get 3I just means go 3 to the right, so it looks kind of like that. And the column vector is 3, 0. Now, using any method you'd like, tell me what you get when you do R plus C. Remember, I can move those vectors anywhere I want as long as I keep the angle going the same, or like the direction, and I keep the length the same. I can move them around. Do it in position form, like draw a picture for me first. And then I bet you'll see the answer is really easy if you just use the column vectors. Okay, here's R plus C, because C is, it's the same thing if I move it right there. It's the same exact thing. So then, I'm doing R plus C, and I get this new answer. I'll make it a dotted line here. And that answer could have been summed up as over 1, 2, 3, 4, 5 spots and up 2 spots. And so I could have summed that up as the answer is 5, 2. How could I have got that really easy? Because 2, 2 plus 3, 0 makes 5, 2. Super easy. Okay. Now, let's see if you can do another one that's without even having to draw the picture of it. What do you think 3R minus C would be? Drawing that picture would be a pain in the butt, but I can make 3R minus C happen in seconds by just going, well, we've got it already. Okay, 3, 2, 2 minus 3, 0. 3 times that minus that. So this comes out to 3 times 2 makes 6, 3 times 2 makes 6, 6, 6, minus 3, 0, which makes 6 minus 3 is 3, 3, 6. What does that mean? That means the vector that would go from 0, 0 to 3, 6. Over 3, up 6. Right there. That vector would be the answer. Why? Because if I took 3 of these, 1, 2, 3, and then went back one of those. Oh, that's right. That wasn't R. I do 3 of these. 1, 2, 3, and then go back one of these. It'd be there. That's the quick sketch of it. All right, let me show you how easy these can be. We'll continue the pirate theme. We'll do P for parrot, or pirate, is 6I minus J. And on the other shoulder of the pirate, often there was the small monkey, at least in Jack Sparrow's day. And that would actually make some sense. Those little spider monkeys are all over those Caribbean islands that the pirates were famous for sailing around, so it wouldn't be too surprising. Feed them enough little banana chips, he'd probably be your friend. 2I minus 5J, and then tell me what 2P minus M is. And use column form, be way quicker. Don't draw me a picture. It would take you forever. But if you just use column form of this, it should be snap, snap. Pausing for a second. Just so you don't go too far wrong, here are the column vectors. 6, -1, and 2, -5. Those are your little column vectors. By the way, the most simple vector, column vector, is 0, 1, and the other one's 1, 0. Do you get that's just like 1 in the x direction and 1 in the y direction? Those are called unit vectors. Unit means 1. You know, unit circle at a radius of 1. The unit vectors just have 1 in each direction. One, they could have this little unit vector and that little unit vector. This one goes 0 in the x and 1 in the y direction, which means that one's an up and down. This is an up vector, I guess you could say. All right. So, did you go 2 times 6, -1, minus 2, -5, and that just makes a little equation. 2 times 6 is 12, minus 2 makes 10. And 2 times -1 makes -2, minus -5 means -2 plus 5, which makes +3. Raise your hand if you had 10, 3. Okay, good. There you go. You learn new stuff. Now, let's get to the homework so you can see the stuff in action, what it's going to be like later on the actual tests. Oh, one more thing. One more thing. And this is not hard, but you need to understand it. Do you get, if that's the x and the y-axis, what would the z-axis be? Comes straight out at you. So if I wanted to say 2, 3, by now you should be able to go, oh, so you're saying over 2 and up 3, dot here, and it's a vector that goes like that, right? What if I say 2, 3, 7? Then over 2, up 3, and it comes back 7 towards you. Imagine this dot coming straight towards you, 7. Let's say that's like out here. I'm showing the marker going straight out from the board. And then the ray would go from here out to the tip of the marker. And it would be this, I'll put another marker here. It'd be like this blue marker then coming from there and going out towards the tip of this marker. So there's the final answer. It's a ray that's a little bit longer than the length of this marker. It sticks out kind of up towards the projector over there. That make sense? That's how you get a 3D vector. But when you're multiplying them and stuff, it doesn't get super hard because you don't have to draw them. I just go like this. Would you understand how to do that? Yeah, it's not too hard. Times the first set by 2 and then take all those numbers and subtract the blue ones from them. All right. So how does this get more complicated? Of course, we'll make it happen like this. Let's say we put in an A there because we don't know what that is. And let's put another number down here and make it a Y. And then say it equals 16, 20, and -30. Do you get, I can write little equations then for that? 2 times 2 is 4, minus -1. 4 plus 1 is 5. That'll be a 5. Sorry about that. But this next one had a variable, so I can make it anything I want. So 2 times A minus 2 has to equal 20. You get I can solve that for A, figure out what A has to be. So it's a way of giving you an equation by giving you vectors where we don't know some of their parameters, some of their XYZ. All right, so that's as complicated as they get. Now let's get to the homework. It's day 3, and we are going to be just skipping number 6. So this first few, I hope you're going to find laughably easy now. Tell me the column vector for B, and then we're just going to triple it. What's the column vector for B? 4, 7, 5, and then you just triple it, and you got your answer. It's that easy. Okay, II, which is a good one for being the naval theme. II, Captain. Ooh, on that quick note on that naval theme, the Air Force. I might have to do a math behind it on this one, but it was interesting quote. GPS is one of the Air Force's best weapons. Why? Did you know that all GPS is controlled by the U.S. Air Force at a facility in Colorado? Just think about this. If the U.S. has some way to keep GPS working for the U.S., but not for others, you get how that could change things in a war situation? Let's think about the ramifications of that. If only you had GPS. Like ships right now are all directed by GPS. I mean, can you imagine the insanity that would ensue? I wonder if other countries are going to develop, maybe they already have and they just haven't like told everybody, but they're going to develop their own GPS systems with their own, you know, satellites and all that stuff you need to control it. That's an interesting thought. Yes. You couldn't use if the Air Force had not released it, and they released it to the whole world to use, if they had not released GPS, you know, like if that wasn't, you know, like somebody's controlling it, right? No, it's the Air Force. They got a facility in Colorado that controls it. Yes. Okay, but if I told you the coordinates were at 23, 47, 912, then that's a spot, but how are you going to know how to get there if you don't know exactly where you are at any given moment in time? So basically there's satellites that are coordinating all of it, and a big, apparently well-guarded facility in Colorado that controls it. But oh my gosh, there's all kinds of craziness that can ensue when you start thinking about that, because then what if the bad guys could get control of your GPS? Or what if they just bomb the snot out of the facility in Colorado? Would all GPS go down? Okay. Sorry. I'm blue-black colorblind. Okay. So your homework for today has some easy ones like these. Number 2, don't overthink it. It's just like number 1. It just uses letters like OA instead of B. So number 2 is extremely easy also. Number 3. Number 3 is just added a third dimension to it. And it's the same exact thing. If you're just going to triple this or times it by -3, you just slap a -3 in front of this and you do it to each item. This is called a scalar. Notice it is not a vector. It's just a number you're multiplying it by. That's called a scalar, a scale factor. Okay, so those will be easy. This next one, this is just saying in words that it's 2 vectors. See, vectors with an S. It's not just a vector that goes from here to here. It's 2 separate vectors, A and B. And let's say A is down here. And let's say B goes up here. And it's the vector that goes to this point and the vector that goes to that point get added together. How do you add vectors that are going opposite directions? That's what you have to figure out. It's not that hard. You can do it. It's just asking it in a funny way. This is good stuff. It's making you think about it. If you wanted all problems that were this simple, you certainly shouldn't have taken honors pre-calc. Okay, on to this one. Again, it says it in words. It's just a different way to get there. Question first. Good question. If it doesn't say, I would, oh, this one does say, but even if it didn't, I would use column vectors. They're just so much faster. All right, moving on to this. 5 is a good one. It's got some words. It's just a 1-minute question, not too bad. Number 6 is just extra practice. That's a little too easy. You just change them into column vectors, and it'd be too easy. So you might skip 6. On to 7, or 7, there is no 7. Number 8. This one's that kind where you get an equation. Some number I don't know times 774 minus 3 times 3, 1b. Hear where I'm going here? It's going to make you a big vector problem that you can make equations for. So then 7 times a minus 3 will equal whatever's over there. I'll let you, if I do any more, I'm doing the whole problem for you. So just write it out as column vectors, and equations will emerge quickly when you solve the equations. Same with number 9. It's just, again, a different way to say it. There's a lot of ways to write these vector problems. And the 8 and 9 are basically the same thing. And number 10, which is a actual real-world problem. This is a good one, and this is more like what the test will be like. And that's why we still have time to get there, so that you get these basics under your belt. Like today had a lot of basics in it. Half the test is like today, or it's in the format of today with like column vectors and position vectors and stuff. Okay, so if you get what we just did today, you're well on your way for the test. But if you can put them into real-world situations where you can say, oh, well, that'd be kind of like a column vector of this, this, and this. If you can make column vectors for number 10, then the problem will be easy, and you'll say, oh, actually, that's not that bad. Okay, that's all I got for you for today.